Welcome to The Explainer. Today, we're diving into something that is honestly absolutely fascinating. We're looking at a brand new report called Electromagnetic Transient Modeling of Large Data Centers for Grid-Level Studies. Now, this incredible piece of research comes to us straight from the Pacific Northwest National Laboratory, and it was prepared for the U.S. Department of Energy. I am so excited to guide you through this, because today we're going to explore the invisible electrical heartbeat of modern data centers. Think about it. Every single time you stream a video, query an AI, or mine some crypto, there's a massive physical infrastructure on the other end that literally has to pulse with electricity. And as we're about to see, that heartbeat is getting louder, it's getting faster, and it's getting so much more complicated.
Right off the bat, this brings us to a really provocative question. How do you protect the power grid from a hyperscale AI data center? We're seeing these massive artificial intelligence facilities being built right now, and they're creating truly unprecedented power demands. We're talking about energy consumption patterns that have grown so much in sheer magnitude and complexity that they're actually creating massive blind spots for our grid operators. It's a huge deal. If we don't figure out exactly how these digital behemoths interact with our physical grid, we risk some really serious stability issues down the line.
Okay, let's dive into this. Here is our logical roadmap for today. Number 1, data centers versus the grid. Number 2, modeling the digital behemoths. Number 3, data centers of today. Number 4, the hyperscale AI future. And finally, number 5, protecting our power grid. Let's get started.
Section 1, data centers versus the grid. As the report clearly points out, the sheer magnitude and complexity of data center electricity use is actively threatening the stability and dynamics of our power grid.
So how do you actually test a massive dynamic load on the grid before it's even built? Well, to solve this problem, engineers at the PNNL created something absolutely vital. It's called the Data Center Model Library, or DML for short. They basically built this library to give the industry a safe digital sandbox to play in. This way, operators can study these impacts safely and don't accidentally plunge a whole city into darkness while they're running a test. It acts as a foundational starting point to see exactly how different data center components are going to behave when they're hooked up to the wider power grid.
Section 2, modeling the digital behemoths. Now we have to ask, how do we actually study these complex, massive facilities without accidentally bringing the real electrical grid down?
The answer to that is EMT, or Electromagnetic Transient Modeling. I like to think of EMT modeling using a medical imaging analogy. It's kind of like an MRI, but for the power grid. Instead of just looking at the outside of a data center building or, getting a simple average of its power use over time, EMT modeling lets operators peer inside. It lets them see the rapid, invisible electrical transients and fluctuations that are happening in fractions of a millisecond. It's one of the highest fidelity forms of modeling used in power systems today, and it is absolutely crucial for understanding modern power electronics.
So, the crucial point is understanding what a UPS is before we go any deeper. Distilling this jargon down, a UPS, or uninterruptible power supply, is essentially the battery backup system. It ensures continuity of power for the server racks if the main grid ever goes down or experiences a hiccup. Getting this definition out of the way right now means you're perfectly prepped for the engineering deep dive we're about to take.
Section 3, data centers of today. We're going to start by looking at the first half of the 6 data center designs outlined in the report, starting from the simplest setups and building up to progressive complexity. Let's look at Design 1. This is the simple data center, and it's primarily used for crypto mining. Now, why simple? Well, if a crypto facility loses power for a few minutes, someone just loses a little bit of mining time, right? It's not at all like a hospital going dark or a vital cloud service crashing. Because of that, this design uses a very simple 240-volt AC to DC conversion at the server racks, with absolutely no UPS or backup generation. None. It's cheap, it's bare bones, and it's entirely dependent on the grid's immediate stability.
Now, what's really interesting about this slide is the contrast here. On one side, we have Design 2, the centralized UPS. This is your classic, reliable Tier 3 standard for most modern data centers, using massive, facility-wide battery setups. But on the other side, there's a newer philosophy entirely, Design 3, the distributed UPS. This setup, which is notably used by companies like Meta, doesn't put battery backups in one giant central room. Instead, the batteries sit directly at the individual server racks. This saves significant costs by eliminating massive central conversion equipment, but, as you'd guess, it definitely requires some incredibly smart automated protection schemes.
Section 4, the Hyperscale AI future. While today's setups are impressive, AI requires unprecedented power density. We're talking future single GPU racks projected to demand up to 1 megawatt each.
To actually hit that extreme power density without losing efficiency, we arrive at Design 4, Low Voltage Direct Current Distribution, or LVDC. Hyperscale AI is literally forcing the industry to completely ditch traditional AC networks inside the data hall. Converting AC to DC at every single server rack just creates way too much heat and wastes a ton of space. So instead, the facility converts the power centrally and feeds 400 volts or 800 volt DC directly to the server racks. It's a massive, massive leap forward that is completely driven by the extreme needs of AI hardware.
And this brilliantly illustrates the near-future Design 5, the Medium Voltage Solid-State Transformer, or SST. To pack even more power into an even smaller footprint, engineers are replacing those bulky standard magnetic transformers entirely. The solid-state transformer directly steps down medium voltage power straight to DC for the racks in one highly efficient step. This is a real game changer and a major research and development focus right now.
Finally, we reach the totally futuristic Design 6, medium voltage DC distribution. In this setup, even the facility's medium voltage distribution network becomes entirely DC. That means removing heavy AC switchgear and traditional circuit breakers almost entirely from the critical path. It's going to require a massive supply chain evolution, for sure, but it just proves how radically artificial intelligence is reshaping foundational power engineering.
Section 5. Protecting our power grid. Now we have to figure out how all these rapidly evolving data center designs actually interface with the physical power grid.
Let's move to and see how this builds across the different designs. When we look at this summary, a super clear pattern emerges for the AI hyperscalers of the future. Notice how designs 4, 5, and 6 all use a 3-phase active rectifier? What you really need to take away from this is that future AI data centers are going to interface with our grid almost identically to inverter-based resources. Think large-scale solar or wind farms. That is a completely massive shift in how grid operators have to manage them.
As you can see from this timeline, data center design is an incredibly fast-moving target. The transition from traditional UPS systems to direct current distribution and solid-state transformers isn't happening over decades. No way. It's happening over a span of less than 5 to 10 years. This blistering pace is exactly why the DML modeling tool created by the PNNL is so absolutely critical. Grid planners simply cannot afford to wait for these facilities to be built to understand them. They need these models to simulate the future right now.
Let me just read this direct quote from the report because it really hits the nail on the head. Evolution in data center power electronics is being driven by AI hyperscalers. It's such a profound realization. AI isn't just a software advancement confined to code anymore. It is the sole catalyst pushing the physical, metallic limits of our entire global electrical infrastructure. Which leaves us with this final, incredibly provocative thought to ponder. As AI hyperscalers completely rewrite the rules of power, is our physical grid actually ready for the invisible digital demands of tomorrow? Thanks to the amazing modeling work being done by the PNNL and the Department of Energy, grid operators finally have the tools to start finding that answer. Thank you so much for joining me on this explainer today. Keep learning, keep questioning, and I'll catch you next time.